Hi, folks. I'm going to run through these questions in the packet, the review packet. A couple of doozies for sure. One, I'm still not sure I'd like any of their answers, um, but we'll see. A lot of them that are kind of cut and dry. So, here we go. Ready? Number one. This to me is a work is delta KE question. So work is 1/2 m v final squared minus v initial squared. That's how I would do it. 750 joules. Okay. Question is how much work done. The thing slows down. Work is delta KE. Next. 2. Work done pushing this thing. This says that we're pushing something up here, and it says that this is 5 meters. Work delta GPE. mg delta H, right? It's not 5 meters here. It's 5 meters. It says 5 meters high, right? So, hey, boom. Okay. Well, let's see. We can do it like this. Work is F times D, newtons per, or Newton times meters, Newton meters, or kilogram meter per second squared times meter. Well, that's kilogram meter squared per second squared. So that's mass, length, over time. See? I'm not writing the numbers up here. 4. The vertical force acts on a thing with a horizontal displacement. Nothing. 5. Let's see, 5,000 kilogram runway, how high? So this is a conservation of energy. Boils down to this. Whoops. Meters. B. Yes. Go ahead. 6. How far will it travel? What am I doing? This sounds to me like one of these. Yeah? That might turn into one of these. Yeah? How far will it travel? D is, well, mv squared over 2. There's the kinetic energy. F. Really, this is KE final minus KE initial. That's 0. So this is really the initial. The negative sign, don't worry about that. It means that if D is this way and F is this way. So that's where the negative comes into effect there. And that gives you C, 90 meters. Good? Good. 7. 7, I don't love the answers. I feel like all these things should say cosine. Right? We've done this till we're blue in the face. Here's theta. Swings to here. This height is L minus L cos theta. If you don't know that by now, you haven't been paying attention. Go back in your notes. It's there, I promise. So we want, let's see, the maximum velocity. Well, this is one of those. mgh initial, 1/2 mv final squared. That stuff goes in there. 2g. Oh yeah, we can pull out the L, 1 minus cosine theta. I call that none of them, but A is the closest. Unless they're doing some crazy trig identity, which they're not. They're just getting it wrong. Next. 8. Come on, dummy. 8. Frictionless change in kinetic energy. Well, we're going to go from this thing having GPE here at rest to KE here. Its change in kinetic energy has to be equal and opposite to its change in gravitational potential energy, if energy is conserved. Therefore, how much gravitational does it have here? Well, mgh 9. Let's see, how much work is done? 10 centimeters. Constant 0.01 newtons per centimeter. Work is a change in potential energy. So that's P. Don't forget to square. Yeah? Good. 10. What's the spring constant? Let's see. Sorry. 1 Newton kx. Meters. Ah, but they want it in centimeters, dummy. So we leave it as this. 20. 0.05 newtons per centimeter. Next. 11. Which of the following is true? D is true. Has to be true if total energy is going to stay the same. Next. 12. Ooh, what's this? PE versus F. Well, F. We got to know the PE versus X one. You have to know that. You have to. Looks like this. Well, F is Kx, so it's basically X, but just multiplied by a constant. So it also looks like that. B. Remember, this one, what's this one? Oh yeah, that's F here. Good. Good. 13, huh? 13. This is the one that, one of them that I don't like. 5 identical masses. We'll call this 5m. Stretch this spring, I don't know, let's say it's initially like this, by a distance L. So spring constant K. 3 of the masses are removed. Well, here's what I know. Now it's 2m. This for sure is now going to be 2/5 of L. Right? If 5 masses make it stretch L, then each of the masses make it stretch 1/5 of L. So with 2 masses on there, it'll stretch 2/5 of L, or 2L over 5. Yeah? Okay. What's the potential energy stored in the spring? Well, 1/2 K x squared. Well, what's K? K is F over X. Right? From F equals K times X. So K, in my mind, is 5mg over L. So we go, now K doesn't change no matter what. K is this, doesn't matter at all how much it's stretched. So we write that as 5mg over L times 2/5 L quantity squared. That's, well, 5mg over 2L times 4L squared over 25. Okay? So that's 20 mg, well, how about this? 20 mgl over 50. So I call that 2/5 mgl. I don't see that answer. But I say it's 2/5 mgl. That's what I'm going with. It's closest to C. I think they just got it backwards. There's my answer. 2/5 MGL. All right, so 13, question mark. 14, let's see, horizontally, we have, well, 1/2 kx, whoops, initial squared, 1/2 mv final squared, conservation of energy. Well, it's the other way around. This is final. This is an initial. The bullet shot into the spring. Fair enough? So what was V? V was kx squared over m square root. Kx squared over m square root. Oh yeah, so we can make that, take out the x. Hey, that was 14, 15. If V here, you should be able to prove to yourself that after falling a distance h, that's how fast something goes. Kinematics and or conservation of mechanical energy. Well, when it's gone to, when it's fallen a distance half of h, that's the same as that. Well, we said this is V. So your answer, V over square root of 2. Hey! Next. 16. Vertical. Vertical. Spring is depressed. What's the maximum height? Well, we're going to have this. And then we're going to have this. So we have 1/2 kx initial squared mgh final. Max height. Okay, x squared over 2 mg. A. 17. Dig it, dig it. At the beginning, when this thing's at rest, right? Released from rest, potential energy equals a total mechanical energy. Because, remember, kinetic energy is 0. Tells you on the graph, 25 joules. Mechanical energy total is always 25 joules. When it's at point D, notice its mechanical energy is, sorry, its potential energy is 15 joules, which says that KE has to be 10 joules. How fast is it going? Solve for V. C. 18. 19. I spelled brakes wrong. Duh. 20. B. 21. Impulse, area, impulse, area, F, T, impulse, F average times T, impulse, area, C, 22. Objective, what's its momentum? Okay, after time T, well, momentum, mv. So the question is, how fast is it going after time T? Drops from rest. V is G times T. Well, that would be C. Check. 23. Let's see. Oh my, how do we do this one? Compressed 20 centimeters by that. Spring is released. What's the impulse imparted? Oh my. Well, let's see. I think what I did here, yes, was I did a conservation of energy. it's going to end up going that fast, V naught or VI is 0. So that means that if we want the impulse, it's really just that. Okay? See, that's what I get. Boom, couple rapid fire ones. 24, C. 25, B. 26, D. 27, still working on it. 28, I got a feeling 27, I got a feeling that 27 is a two equation, two unknown thing. Because they're saying that they conserve all their kinetic energy. So they're saying it's an elastic. It treats it like an elastic collision. So we got to crank through that two equation, two unknown thing. The answer it gives in the, what do you call it, in the key is D. I haven't gotten there yet, but I wanted to make sure I get this out there. 28, football in space. Why not? Well, we get this. No, that's C, right? No, I think it's B, isn't it? Yeah. Yeah, B. Wait. 28. A. No way. T says A, but right? I mean, give me a break. This is M1, V1 initial is 15, whoops, kilogram meters per second squared over, well, 50 and a half kilograms. Well, that's, as far as I can tell, B. Good? Good. 29. Okay. Ooh, 30. 30 is awesome. 30. Here's what we got. M. Moving this way. 2M. At rest. Yeah? 3M. If this is V, you get that this is V over 3? Does that work for you? 3 times the mass, got to move 1/3 as fast. How much, what's the change in kinetic energy? Well, here, total kinetic energy is 1/2 mv squared. Here, total kinetic energy is 1/2 3m v over 3 squared, which is 1/2 3m v squared over 9, which is 1/6 mv squared. Yeah. We started with 1/2 mv squared. We go to 1/6. Well, this is 3/6. Wait a minute. Oh yeah, sure. It starts as 3/6 mv squared. It goes to 1/6 mv squared. The change is 2/6 mv squared, or 1/3 m. Come on, 1/3 mv squared. That is C. Love it. 31. Ah, speed of the cars right afterwards. B. 32. Love this one too. Let's see. 32. 1 kilogram. Moving this way. 2 meters per second. Let's just call it this. Oops. N. V. Hits what? 5M. They stick together. It's 6M. Moving now, V over 6. Yes? Okay? Okay. Ratio of initial kinetic energy, which is that to final kinetic energy, which is this. Well, that simplifies to mv squared over 6. Well, look, the only difference is this one's divided by 6. Ratio is 6 to 1. 33. A. 34. D. 35. D. Boom! 20 minutes. 35 questions. That's what I'm talking about. That's a lot faster than you'd have to go in the AP exam. But yeah, well, who cares, right? If you have questions, folks, let me know. Let me know. I'll work through that one. Which one is that? 13 or 14 or something? No, it was the jousting question. Whichever one that is. 27. I got to work through 27. All right, folks. I'll see you tomorrow. Or see you when I see you. See ya.